Okay, let's start now with a very specific part. Models are considered to be instruments in a scenario. Since the model is an instrument, we should also think how to master instruments. And for this reason I come now down with model engineering. Model engineering includes a number of topics we have been already discussing, at least in part 3, starting with lecture 11. Now we go for, let's say, engineering of models. As already said, engineering is somehow an orthogonal concern. We should have a sufficient quality as we require also for the bendability of models. We might have to live with errors and failures. We are living with deficiencies, so we have maybe some restrictions according to how we have been mastering a model. We have maybe to provide somehow a facility for a proper cutout, for proper focusing, and for this reason we have some kind of forgetful representation. And of course it is user demand driven. So the plan is now to come in one of the last lectures to model-based reasoning, to model-based problem solving, to model-based reasoning, and to model-based engineering and living. That means in this case we would like to have a proper representation how we can use a model in order to reason based on models. In this chapter I will now talk about the so-called Konstruktionslehre, or the design of models, and before we have to consider the language, the tools, the change, and the quality management. That means in this case we have now a number of topics to cover whenever we talk about model engineering, as it is maybe also true for instrument engineering or instrument production. In this case, of course, the problem is really that we didn't consider so far really what is engineering. That is, in our case, a cross-disciplinary approach to development. And in this case, we have, of course, to look what we want to have, how we can support it in a proper way. And this is the same as we do in computer science. Quite often, however, computer engineers are not looking for what a user wants. They are looking for what a system does, maybe based on some kind of requirements we have been somehow detecting. In this case, of course, we want to have a little bit more than what classical engineering does. Okay, what is now engineering in this case? Engineering in general is some kind of systematics of techniques to imagine, to design, to create, to make, to operate, to maintain, and to dismantle. That means in this case we have to think about skills and trainings and practices and experiences we should somehow use in our model engineering. Engineering in this case has a meaning that it is the art, the science, or the craft of changing a dream into a reality through conception, feasibility, design, manufacture, or construction, to operation, and eventually later for removal and retirement of a model. In this case, as already said, it is a discipline that covers quite a lot of different activities we have in our disciplines, in our engineering, and maybe also in daily life. It is also based on some kind of intuition. I have said in chapter 1 already and cited somebody who said, and engineers build systems and solutions without asking the somehow useless question why it functions. The main thing is it should function. Engineering includes also design as Konstruktionslehre, and we have a number of engineering functions we are supporting, or we should support, at least for modeling. And of course we have to handle all different phases: development, deployment, maintenance, evolution, and of course also finally retirement. There are several major engineering functions we should consider. One is research, using some kind of mathematical and scientific concepts, experimental techniques, and inductive reasoning. The research engineer seeks new principles and processes, so that it will be something like in design science the Rieger cycle. We have second, development. That is a typical thing what we do all the time in engineering. We have design. That is somehow going back to the well-formedness of models, so that the model can really be properly used and used according to the quality criteria we have been considering. We have construction as construction of a product or of an instrument. We have production, and we have also, of course, also some kind of model usage, that means operation, and of course management, and maybe other functions as well. In this case, we have for model engineering something what is performed before model formation, that means during the landscaping and initialization phase. That is performed maybe during model formation, that is typically true for model development and model construction, and something that is performed after model formation, that means during the utilization phase. In the later case, we have maintenance, maybe based on modernization approaches, model evolution. Modernization includes, of course, migration and, of course, also some kind of revolutionary stuff like removal and cannibalization. It should also, let's say, somehow use for compiling the experience we have gained so far. So that means it's similar to the Rieger cycle of design science. And we have maybe a guiding deployment as well. In the first phase, before model formation, of course we have some kind of feasibility studies. And of course we should investigate which model space is really available, what are the alternatives, what kind of decisions we have to make very early, what kind of principles we should follow, what kind of deep model we should reuse somehow. That means in this case we have something like the landscaping for model engineering. And then we do our classical construction with anything what is somehow done for construction, as we did in the chapter 12 of this lecture series. We have a general approach in engineering. First, we analyze, we compare. Then the next step is typically the same as we do in mathematics. The problem is reduced in such a way that it can be clearly stated, and in this case we can clearly define what is, let's say, the model function in which kind of scenarios, and what is not the model function in that scenario or in other scenarios as well. What kind of scenarios are not considered. And then of course we have some kind of answering, and answering means in this case we use reasoning methods or we use some kind of design, and then we have finally maybe a faithful model where we can really have a solution for the problem we have been stating at the beginning. That means in this case we can go for engineering or model engineering maybe the same path as people do in systematic engineering. It is not yet done so much in computer engineering, but it can be also handled in this case. What we have in this case maybe is some kind of 6 layers of systematic engineering. First, we get a description. The description of constructions, of rules, of runs, and schema, declaration, anything else what we want to have. The next one is we have some kind of control mechanism. In this case, we can use some kind of, let's say, operational semantics or methods, rules for handling, strategies, and maybe auxiliary methods as a technical support. After being ready now, we can say, okay, fine, now we need to integrate it into the complete environment. That means in this case into the technology that we have somewhere available, and of course also into the applications. Then we have a fourth layer. The fourth layer, like in an onion approach, is organizational layer. We try to establish what we have been doing in such a way that we know what is now the whole system we want to develop, or the whole model suite we want to develop. And finally, we have also some kind of restriction. I would call it economical layer. That means in this case we say, okay, fine, what is feasible, what kind of quality we want to reach as a minimum, and what is never achieved, or what we never have as a target for quality. That means in this case we have some kind of stop sign. And finally, we should have some kind of layer, what shall be done in future, how a model is somehow improved, like we do it with instruments, how a model can be optimized, how a model can be transferred whenever a new technology is available. A typical case are classical finite methods models. Long time ago, it was realized that finite methods models are not pretty easy to compute, and for this reason, with our restriction of computers we have had at that time, we said, okay, fine, these methods are not supported, and for this reason maybe we should use another model set. Later we realized that we have now supercomputers, and for this reason we can be very quick with anything. So that means in this case we have, of course, a good, let's say, part for the evolution. Then in this case we could have for our model engineering some kind of meta model. This meta model is mainly targeting on facilitation. Facilitation is based on a number of phases: inquire, investigate, vision, analyze, qualify, plan, apply, report. We have also some kind of needs for sense making, and in this case we should use some kind of methodology that allows to integrate concepts. Maybe you have to conceptualize a modeling solution, we have to enhance maybe the conceptual schema by modeling templates, we have to develop control and measurement practice, we have to maybe develop a parameter set that is reducible and depends on some kind of representation techniques. We have maybe techniques for performance analysis of the model according to the criteria we have been using for our statement, what kind of model and what kind of function should be supported. Furthermore, we should think of methodologies. Methodologies we have been already discussing in chapter 11, for instance on the basis of database model development. Methodologies are nothing else as specific workflows that function in such a way that we reach what we want to achieve, what kind of function a model should have in the given scenario, and what kind of, let's say, support the model provides to these scenarios. Therefore we should have some kind of methodology. I will not talk too much about methodologies. This would be a separate chapter for model engineering. We have a number of tricks. In the box of tricks are reference models. Reference models allow us somehow to reuse what we have been gaining so far, what we have been developing so far. Maybe we reuse the meta model, how the model is constructed, or we use, let's say, a model that is maybe a generic model or a universal model, and then we have some kind of facility to use this reference model as an initialization for model in the modeling process, with let's say adding something that must be very specific for this scenario, for this function of the model. And in this case, we can have now generic models of models as a generalization of reference models. In this case, we elicitate relevant structures and processes, of course, for generalization. And in this case, we can say, okay, fine. For instance, in a database setting, we can say name, description, modeling method, modeling environment, keywords and categories are somehow elicited. That means in this case, we have now a generalization path. We can use now this generalization also to describe what would be the specialization of the generic model to the specific model we would like to develop in the future, at least. We can generalize what we have been doing in the Open Model Initiative. We might use, whenever it is possible, a separation of concern, for instance, into static and dynamic basic categories. We might have also an injection of our methodology, and we might have a separation of concern into small units, maybe attributes in the database setting, so that we can have a proper constructed model. For instance, we can have maybe primary dimension in our model definition. What is the purpose or the function? What kind of mappings we are using? What kind of language? What kind of added value we target with our model? We have secondary dimensions. What is the artifact we are using? Which users in the community of practice are somehow participating? What is the context? What is the application domain that we are describing? That is the same thing as we have had with Gregor's taxonomy of theory types in information systems development research. Analysis says what is, explanation says what is, how, why, when and where. Prediction says what is and what will be. Explanation and prediction says additionally how, why, when, where and what will be. And finally we have design and action and say, okay, fine, how to do something in this case. That is the same pattern we can use for our model engineering. Okay, the first part of the model engineering might be to have a sufficiently expressive language. That means in this case we might start with language engineering. Languages are used as enablers, and of course in a model suite especially we would like to have a coherence of languages. This can be based on a mathematical theory that is called institution theory, mainly developed for category theory and mathematical logics. If we use a classical, let's say, model with only one concern, then in this case we should not use a model suite. We can have maybe a classical Thinkel language that we can use in this case. That is pretty well understood already. Quite often in the classics it is said first we develop an abstract syntax, then we have some way to assign symbols to concepts, and thus defining the notation as a concrete syntax. As a third we have maybe semantics. That is a classical separation of syntax and semantics. Syntax first, semantics second. I think it is far too strict. And another critics coming from linguistics is that pragmatics and pragmatism is not taken into consideration. For this reason we should go a little bit beyond that what we have there. We can use an approach that OMG has been developed to language engineering. We might have some meta model that defines a class on congenious models. We have some generic requirements we should consider: correctness, completeness, clarity, unity, and we might target on general purpose modeling languages. General purpose modeling languages might be too general or might be not feasible because of we would like to have a language that is easy to handle, so based on few generic concepts, no account for domain-specific concepts, and often used to support system analysis, design, development. And for this reason, maybe it is usable for almost anything. And it might bridge the gap between conceptual domain models and the respective implementation. That is maybe a little bit too specific. For this reason, we would like to go and say, okay, fine, in which case it is a good approach. Of course, we want to have comprehensibility. So that in this case, anything what we want to specify should be somehow contained in the language. We should have a good foundation and a good tool support. Of course, with the goal that the model is proper. It should be also evolution reliable. That means in this case we can have an extension whenever it is necessary, we can have a modernization whenever it is necessary, and we should be able to integrate things. For this reason, it might be better to use domain-specific languages that allow at least a proper definition according to the domain knowledge we have, that is mainly the deep model what we shall use. That is maybe a bit difficult because of we can have a lot of application cases, and maybe a general purpose modeling language, GPML, would help us in this case. I'm not sure whether it is really possible to do so, because of in the past we have had the domain-specific languages challenge and dilemma. In the 80s we have had about 4,500 so-called Fachsprachen. Little languages maybe is the English expression for it, or application domain languages. And 4,500 meant that is a complete dilemma and a nightmare to select which language is a proper one, which language can be supported. I was already discussing that in connection with the depot approach in chapter 14, when we have been talking about models as programs. So in this case we might face the same problem. Also, it is somehow advocated by a lot of people. The OMG and the MOF have some kind of layering of what we represent. We have the M0 layer, that should be the level of things. Things can be also models, things can be also objects, and of course we would like to reflect what we have there. And then we have a level of description. Models refer to what we have been considering so far in the M0 level, and they are used as descriptions, prescriptions, reflection, representation, whatever you want to have. In this case you have some kind of modeling abstraction. Abstraction on what is in M0. That means going from M0 to M1 is nothing else as using some kind of abstraction, as we do with our modeling approach anyway. In this case we have maybe 5 different kinds of abstractions we should consider. Classically, component abstraction is considered. That goes back to the first days of database modeling. That means we have a classification and instantiation. Next we have aggregation, decomposition, and finally we have generalization and specialization as some kind of component construction and component abstraction approach. The second abstraction is we abstract from the context. That means also from the localization. In this case we consider architectures, orientation, of course model suites, and models are developed within a suite but also separately, and we have some binding and association schema. Next we have some kind of modularization, encapsulation, hiding abstraction. That is nothing else as reduction, focusing, and proper reflection. then we should consider that our models are used typically by humans. That means in this case we should have at least an understanding how a society is somehow using a model. That means in this case we have some kind of maybe view facility if we are using the globalist design approach. Or we have simply in the localist design approach only viewpoints, and we should try somehow to integrate them. And finally we have also another kind of abstraction, that is foundation abstraction. In this case we somehow inject our deep model, or we agglomerate our deep model, we embed foundations, and we might have also some kind of justification. And then we have maybe a second level, that is the level how we can construct a model. Often it is considered the language level, but in reality it is a level of constructors, and of course in order to be, let's say, to have an ability to somehow use parts and pieces of models, we should have selectors. That means in this case we have nothing else as some kind of construction means. So going from M1 to M2 means nothing else as we should look what kind of construction we want to use and what kind of construction should be supported by which kind of constructors. And we can have also the level M3, that is a level of principles and foundations. Maybe we are using an institution-oriented treatment for language construction. Then in this case we can use it in the same way as we do in mathematical logic. We start with signatures, then we say what is an atom, then we say what is a sentence, and then maybe we have some handling rules similar to those that we are using in semiotics. This would be in this case of course again the syntax first approach. The M0, M1, M2, M3 separation is not applicable to natural languages, because of natural languages are somehow mixing all the levels, and maybe you have M0 for the kind of observations you have been representing in, let's say, your data space. M1 could be somehow far larger because of constructors could be again defined on some kind of language expressions. And of course the level of principles and foundations in natural languages is completely different from those languages that we are artificially constructing. But however, for models this separation into M0, M1, M2, M3 could be a right one. The model could appear mainly on the M1 level, but it might be also usable at the level of M2. We might have other models at the level of M3, and finally we might have also models representing, let's say, systems or reflecting systems at the M0 level. For this reason we need somehow a proper language engineering when we are talking about model engineering. Of course, in this case we start with the scenarios and potential functions of models depending on the application area, with rationally, with added values, maybe accepting cultures or habits that are somehow common in the community of practice. Then we might use stereotypes, as we did in lecture 10 already, for adequacy and dependability, and we might orient on some kind of generalization of members of the community of practice using again the personae concept. A personae is an abstract model of the people or the members of our community of practice, and for this reason we can use some kind of this model for a proper statement what kind of languages are accepting. It also includes, of course, a description of the activities to model, and it includes also the determination of the grounding and the basis. A proper language engineering would also include techniques and methods that can be applied somehow. And it would be nice to have some kind of engineering guidelines on maybe a best practices approach. Okay, yeah, this is a complex task, and model engineering would be not possible if we would not have tools. Therefore, the tools are again instruments, and they are second enabler of modeling. They should support injecting application domain knowledge. They should support whatever is necessary for the scenarios that we are considering for our model. And of course, tools are never universal, and for this reason we need some kind of skills to use a tool. First of all, models are maybe enablers. Tools are also enablers for model engineering, however. We would like to have a really nice modeling tool. We should have also a possibility to include libraries so that we can inherit whatever has been done already. We should support also different development and redevelopment methodologies. We should also support a model suite construction, maybe including various representation models, maybe using some specific syntax, semantics and pragmatics notation for modeling concepts, because we need to have these modeling concepts in a proper form integrated. And of course we need some team support, depending on the collaboration style, especially when the model becomes a little bit more complex, or when a model suite is used for representing different styles, different viewpoints, different ways how to represent our observed reality. And of course we should have some kind of functionalities that are easy to incorporate. And reuse is one of the restrictions we should also consider. That is a pretty large list, but this list is somehow typical for sophisticated tools and also sophisticated modeling tools. We might use the very nice metaphor by Dimitris Kargianis, who observed for specific movies representing Greek culture that we are doing nothing else as writing, shooting and cutting, or maybe conceptualization, realization, implementation, and finally deployment and tooling. That means in this case we should have tools as enablers. Tools come typically with their own tacit knowledge. That means in this case something is already hidden in the tool. We have tacit knowledge incorporated into the tools that follow the deep models behind the tool. We have some thought styles and thought schools represented. We have typically a grounding that comes already for free with the tool, and we have also tacit parts of the basis. Tacit knowledge includes also the to-do part. That means in this case we have specific techniques, mechanisms, methods, procedures, algorithms, habits, practices, restrictions. That means we have to learn these specific techniques. Tools typically come also with test structuring, functionality, simulation, usage, storage, tools, programming languages. And when the tool is used for a longer time, then we have bags of tricks developed in the tools community. Of course we need also to have tools that store somehow some kind of versions and phases, and in this case these what is a version, what is a phase, comes already with a tool. And then this tool somehow guides us how to use the tool. And of course we have in this case also some stiffness and obstinacy of tools, and there is of course an injection of tools deep models. We have been already observing it for the rapid application and database development toolbox. You can it also observe for the EduXX toolbox maintained by the Vienna group of Dimitris Karagiannis. Tools are also used, let's say, when the Tacit Knowledge has been used also for extensions to commercial versions of the RAT toolbox, especially for extended entity relationship models called HERM models. That means in this case a tool is enabling and guiding and restricting us. You can also use reference frameworks as tools. That means in this case you reuse maybe your own experience. You can base reference models on a standardization approach, and in this case you might have high quality models that you can directly somehow reuse. You have of course in this case, especially when we are considering a model suite, a web of stereotypes, patterns and templates. You will have libraries of hints, specs and tricks. You have maybe reasoning tools that you can inherit somehow and reuse, and for this reason you have those referencing or reasoning incorporated into the reference framework. You might have explicit restrictions, capabilities. In this case you have also a network of models with their own capability, and you can maybe use this reference framework for inheriting parts and pieces. Then in this case we could directly go for tooling to a model library that could be somehow inherited and somehow used. A model library, as we already explained, has some founding concepts, some structure and function, maybe incremental ones, representing different facets corresponding. You might have an application context, and you might have also meta models for the model library that have of course also their own deep models, and for this reason you should know them when you are using these model libraries. There is a pretty nice guideline of modeling for the selection of criteria for reference models. You have the expressive power, the level of abstractness, the coverage, especially of information, the relevance for reuse, the comparability, and maybe you have also structural characters of the framework. You have maybe again some kind of relevance for reuse. That means in this case we can use these guidelines for reference of the criteria for reference models. In this case we could directly categorize the framework for reference models. We have static categories like the one I show you here in this picture. You have maybe dynamic categories, and in between you have a methodological maybe framework and methodological categories that somehow are based on methods you would like to use in this case. That means in this case we can say, okay, fine, we can have, let's say, a reference framework, and we can use this reference framework in a number of different scenarios. As an example, you can use it for adaptation of existing models. That means for brownfield development. You can use it for the search for a best fitting model. You can maybe use it for the open model community, and or you can use it for model 2.0, what we have been representing in chapter 14. That means in this case each of the scenarios has some requirements, but we should consider which categories are of importance. The methods part is not important in scenario 1 and 2, but it is really important in scenario 3 and 4. All scenarios, of course, include some kind of history and maturity management. For this reason, we need to consider these in all 4 scenarios. Not in general in any case, but maybe in our 4 scenarios you should use them. And then you need also tools for quality check and also tools for deployment. Quality check means in this case we should be aware of what kind of deficiencies, obligations, failures we might have with our model. We should maybe also have some kind of integrators and translators, and in this case we know now which kind of quality can be achieved through application of a translator. Furthermore, we need of course some diagnostic support. That would not be nothing else as quality checkers according to our specific quality properties, SWOT until clear. Of course, we need somehow a way to extract the capacity and the potential of a model. And then we should have, whenever we are using a model suite, also tracers, controllers, and those apply to manage somehow coherence among models in a model suite. Pretty nice tools are based on our ability to handle a certain number of elements, a certain really small number of elements. Somebody counts that we can somehow distinguish in a display not more than 30 elements. Anything else is a little bit too detailed. And then in this case we need to have some zoom in and zoom out facilities, or maybe zoom in on specific details, on the modeling history, on versioning. We need furthermore a logic, not only one, maybe several ones, for handling adequacy and dependability, in order to be sure that especially the quality is somehow proper for our models. And of course we need also some kind of freeze for specific versions, so that we can say, okay, fine, that is now some kind of development, and then we have a web of models or model versions we could consider. Yeah, and then model engineering should also include change engineering, especially whenever a model is not really adequate or dependable, in some case somehow problematic. We need it also for modernization. We need it also for partial inheritance. We call it maybe cannibalization, like economics people are doing it. We need to have something for integration and for heritage incorporation. That means in this case we should be able, with model engineering, to handle evolution of applications, contexts, communities of practice, and also of the backgrounds. Change management has been nicely developed for software engineering. So in this case we have a number of approaches, and I Sommerville has been somehow separating these approaches into the definition of a change request, into the record, in some kind of, let's say, change evaluation, impact analysis, change cost and recommendation. You need in this case tracking tools. Changes should be somehow reviewed, not by the developer but some other members of our community of practice, or maybe even external reviewers. You should also cope with the derivation history, and last but not least, we should not forget that of course we have to have some kind of version and release management. In this case we can generalize it for model engineering in the same way. using the same 7 points for what change management should mean in model engineering. We have in software engineering a number of strategies how we can use this kind of change management in a proper way so that we can be sure that the next result will be a better one. In this case, we might still have the need to develop guidelines, decisions, systematism, criteria, courses. But in general, you can somehow structure the strategies into maintenance strategies, into transformation strategies, especially architectural transformation strategies, and in some kind of re-engineering strategies. That is what we do also in software engineering, in some way at least. Furthermore, whenever we are talking about change management, you can go back to a pretty old paper by Lehman and Belady that shows some laws of change management. Changes are continuous. Changes are typically also increasing complexity. That means finally we should avoid to have some kind of mannerism, something like mannerism cathedrals that we have been building in the past. And of course you should have some kind of handling the complexity, the size, and for this reason we have to handle the large program evolution. Of course it should be also organizational stable, and it should be somehow still familiar to those who are using that. The same we can say for models. Classical software maintenance in this case means maintenance to repair software faults, maintenance to adapt the software to a different operating environment, maintenance to add or modify the system's functionality. Again, we might use this approach for developing guidelines, decisions, systematism, criteria, and courses for model engineering. In model engineering, we can also inherit what people in the standardization committees have been doing. They have been somehow considering the engineering process as it is and the change management as some kind of orthogonal concern. The same we can do for our model engineering. If we want to change something, then we should have a reason. And a pretty nice framework we have been developing in the past was the category, course, solution framework to change management. You say which kind of category of problem you have, what is the course, and what set of, or even collection of solutions you might use in order to handle the problem. I will use it as an example and especially apply it for engineering processes for modeling processes in the database field. You can say, okay, fine. First of all, there is a need for change because of the specification is incomplete. So in this case, if we are not able to represent whatever or have not been able to represent whatever is necessary, then in this case we have a number of potential solutions. If the knowledge is incomplete, okay, fine, then we should add something. The same is also for incomplete coverage, for macro data modeling, for library integration, for inability to represent, maybe for missing the background data if we are considering database models. That is the first maybe pattern for change management. There's a second one. There is our insufficiency to represent the current knowledge in the application domain. In this case again, we have some reasons, some causes of the problem, and we can use a number of patterns for, let's say, potential solutions. A third pattern for change management would be that we have some live span changes over time due to the evolution of the system context. Again, we can separate a number of causes of the problem and develop a number of potential solutions for somehow resolving the problem. A fourth one, I will have a fifth one as well, is that we have hidden cases. So in this case, we don't see what is maybe in the deep model. We have intrinsic parts that are not visible, and maybe we have a number of maybe pragmatic assumptions, for instance, that we have been using, but being not aware of that. So in this case, we should also look what has been not really explicitly stated and what should, however, be explicitly stated. So my number 5 is, it is also dependent on the context. That means in this case we have maybe to somehow to reconsider, like we did it in the first engineering part of this lecture, what is, let's say, a course, what kind of context is somehow stiffy, what kind of context is somehow problematic, and then we can say, okay, fine, we have a number of approaches that we could use. Again, this is a sheet for showing what we shall do in the database area whenever we have a cause of the problem, what kind of potential solutions we can have there. Then in this case you can now use a general change frame, let's say for database system changes. In this case it's okay, fine, state please the problem, and state it in such a way that it is really properly defined. Then use the category cause solution framework for handling it. Then you have some criteria and measures. You should have also some controllers. You should also know what is the trade-off of developing the solution. Then you can use the solution pattern as a change pattern, so you can apply it somehow. And then you can use also maybe some change functions for the databases. I think I should illustrate a little bit more in detail what that means. And then you have functions, views, and support change mechanisms. Okay, yeah, I will explain it on a simple example. You have an initial model, you say, okay, fine, I have, let's say, a type that represents insurances, and it has attributes, you have constraints, functions, views, and that. That is maybe a little bit too general, and you would like to have a way how to handle contracting for insurances in a proper way and not to integrate it directly into the insurance schema or type. Then in this case you say, okay, fine, what I do now is I develop an intermediate model that can be used for developing the changed model, the final model. In this case you say, okay, fine, the insurance has of course some kind of, let's say, necessity, and in this case we have to use the root facility, create, retrieve, update and delete, to monitor until a certain date. And then we can say, okay, fine, I have now I'm using now this intermediate model as a model that can handle all data changes in a proper way in the old schema and potentially also in the new schema. And then you can have some kind of data coherence. You have maybe a policy, you have maybe a style. In this case you could say, okay, fine, I have a master-slave style, I have some kind of policy based on materialization. And then you say, okay, fine, I might have also redundant data, and since I have some kind of usage deadline for the intermediate model, I have also a finalized date, and then I say, okay, fine, on 30th of August 2012 I have to move to the final model and then to use all in the final model. That is nothing else as a certain strategy for migrating from one model to the next one. That means you have a systematic change management. You can have the same, let's say, if you have something like an offering and invoices, then you can find the invoices have maybe somehow contributing to the calculation of the total amount. But in this case, you say, no. In this case, we can directly handle it with the invoices. Then in this case, okay, you say, okay, fine, I have some kind of intermediate model, try whatever can be used for the transformation, and then in this case, I finally switch again to the final model. You can have also some kind of restructuring. Think about a bit of problematic schema that represents transport activities. You have a trading company, you have to transport goods, you transfer it to a retail store and or to a depository store, and you are using cars. In this case, you might have insurances and bills additionally, and of course it is all done by some kind of transport company. This transport relationship type with 6 components seems to be a little bit too problematic. You can decompose it. You can say, okay, I have for a marketing company a retail store. I have for goods I would like to take a depository store. And these stores are somehow connecting their, let's say, purposes. You have for the retail store the marketing company. You have for the goods the depository store where you have it. Then you might have a transport request. Transport something from this place to another place. And based on this request, you have an event. And the event is using cars owned by some transport company. It is also, the cars are also insured by some kind of insurance, by an insurance company. And of course, the transport event is built. Then in this case, we have now a pretty simple schema for the transport. The transport in reality consists of the request, of the event, and of the bill. Then in this case, the restructuring and the change management would be a decomposition of the previous schema. And of course, in this case, you can use again intermediate models in order to handle the transition for a certain while. Okay. One thing that is very important for model engineering is, of course, engineering of the quality. A model must be of a sufficient quality in order to be dependable. Sufficient does not mean the maximal, optimal and something like that quality. It means only sufficient qualities. The problem is quality characteristics we have been introducing in the quality chapter might be somehow in conflict with each other or might compete. That means in this case we should select what kind of qualities are better to be considered. Okay, then you can say, okay, fine, I do it the following way. I'm looking for a long-term sustainable development. A model should be useful. That means we can now orient our quality engineering on the usefulness of a model. It should be not necessarily true. Truth is not a property of a typical model. It should be only useful. And then you can say, okay, fine, I have a quality management. First, it considers risk and failure management. Then I have maybe a number of quality criteria or categories. And we have been separating the quality characteristics into quality in use, external quality, and internal quality. Again, we have maybe too many characteristics, and we have now competing and conflicting characteristics. The best solution is still a robust solution that is, okay, fine. We select some primary, and for the secondary, we have some kind of toleration schema. What kind of problems we would tolerate for the other characteristics? And we have in quality engineering also to consider the deep model conflicts that might hinder a proper quality engineering. I think the last point sounds a little bit too abstract. Maybe we should consider an example. I will not use in this case a computer science example. I will use some kind of example from the economics area. In Western macroeconomics, we have a main driver, money. Money first, quality later. Oh my goodness. That means in this case that engineering that would be oriented on quality is conflicting with money first strategies. We observe it currently for the shareholder value and the instant dividends, for the orientation on the market value of products instead of utility value of a product. I think you should pay not what a market gives you, you should pay for what kind of utility a product has. Utility orientation is typically for engineering. Market value is typically for money first economics. Then you have also something like a maximal profit is far better than a long-term optimal behavior. That means in this case we have also a number of problems that directly contradicts our engineering criteria. Macroeconomics is also not oriented on sustainability of products. Products should not be repaired, they should be directly replaced and you should buy a new one. Then we have an assumption of continuous growth of anything that conflicts also with engineering, because if you throw away whatever is useful, and in this case you have a number of problems. First you consider the profit and anything else comes later. Then in this case, with this kind of macroeconomics, you look for optimizing supply chains worldwide. And whenever in the chain crashes, fails, then in this case you have a lot of problems somehow to maintain the whole chain for the product. Furthermore, we have some kind of assumptions for equilibrium that is typically somehow expressed by these St. Andrews. In economics we call it Marshall's cross. We have some rationality assumptions for the customer choices that is also in contrary to engineering criteria. We have also some kind of education outsourcing that is coming with all these parts, and you have some cycles in crisis management for monopolization. Then you have also for microeconomics a number of conflicts to consider. This is maybe best expressed by one of the wise economics people. The economic sciences are characterized by the ability to analyze with scientific precision why their predictions were wrong. Okay, then it comes now that we have to have some kind of quality engineering based on resolution of conflicts. I would prefer even to use robust models. You have some measures of tolerance in this case, and you say, okay, fine. For modernization, you know how to manage it. You have also some kind of aftermath prediction of model utilization and restriction of model application. And you have a separation of quality characteristics into secondary, tertiary, and so on properties. And you have, of course, proper characteristics that can be evaluated. Okay. Another part of model engineering is design. Design should be a real apprenticeship. And for this reason we need techniques and methods for developing high quality, at least in such a way that there are sufficient models. You can use a number of design concerns. 3 U's: usefulness, usability and usage. You can also use a methodology that says form follows function. Manierism might be nice, but is completely useless. You orient on usefulness. You might develop componentization and standardization so that you don't consider proprietary solutions. You have robustness of models, and you have some design principles you should consider. One main part in the design is the orientation on utility, and for this reason the orientation on significance. In design approaches there is a dictum stated by Lehman. He said, form follows function. That means we are oriented on models that are functioning, and the form should support it. And then you can say, okay, fine, for acceptance of the model you need some kind of significance that explains how the form assumes a meaning in the ways that the model is really properly usable. Sometimes the form is a bit problematic and maybe is misleading you, as we have been already discussing in our case studies, chapter 2. The meaning might vary, the cultures might matter, and for this reason we should use maybe something what Bernhard has been doing for the meaning of things. Okay, finally we come now to the apprenticeship, journeyman and master craftsman. Apprentices are the first stage, but what you would like to have is some kind of fellow craft mason for model engineering and mastering of that trade. In this case we have now reached what should be done about our model engineering, as including a Konstruktionslehre, design, proper management of model, making of model usage. So we come now down, or can now close our model engineering section, waiting for the next section, that is considering foundations of modeling. We would like to have a really modeling discipline. Modeling should be well-founded and systematic activity with its backgrounds, foundations and techniques and background. Okay, section 17 will be now a bit systematic on the, I would say, philosophical part of our models, and later we would like to go to the mathematical support of models. Thank you very much for this lecture. We can now go, after having somehow deeply discussed the first part, the second part and the third part, to the foundation part. Or we can open our champagne bottle and say, okay, fine, part 1, part 2, part 3 is sufficient, and the foundations part can be somehow accepted, and for this reason it comes on the last place.